So we have completed the data transfer group instructions, and now we'll be starting with the second group of instructions, that is the arithmetic group. So in the arithmetic group we have 20 different instructions that we'll be studying. As compared to the data transfer group, the difference here will be in terms of the flags that will be affected. In the micro RTL, definitely the instructions are different on a but there's not any special type of instruction where our micro RTL will be different from that of the data transfer group. It will almost be similar, the same opcode fetch machine cycle, the same memory read, memory write machine cycles. So we'll be seeing. So the first instruction that we'll study under this group is Addr. So what does this do? This, as I have pointed out previously also, in all the arithmetic instructions, in almost all the arithmetic instructions, one of the operand will always be in the accumulator, while as another operand can be in the memory or in the general purpose register. So one operand is always in the accumulator. So what does this instruction do? It adds contents of register R with accumulator, fine, and stores the result in the accumulator. So you have this instruction add R. So what this instruction does, you are adding whatever is in the accumulator with whatever is in the register, and that what the result will also then be stored in the accumulator. So you are adding two operands, and the resultant one operand is in the accumulator, one operand is in the register, and the result will be stored back in the accumulator. So the number of data bytes that this particular instruction will consume is, it's a single byte, fine. So you have 1 byte for defining the opcode of the instruction ADD. There is no data that is provided with this system that will actually be consuming memory space, so it's only a single byte instruction. The data are in A and R, they are internal registers of the microprocessor. They are not consuming any space in the memory of the microprocessor. So number of machine cycles, it will be one machine cycle. We have to read, we have to decode the opcode. So you have one opcode fetch machine cycle. You have to neither read the memory in this case, nor write on the memory, nor read an input device, nor write onto an input device. So only one machine cycle. F 4T states. The opcode fetch machine cycle obviously takes up only 40 states. G, the execution time, 4 into 0.32, that is 1.28 microseconds of execution time. H, you have 7 variations. Seven variations. So the examples of these variations, you simply have ADD A, ADD B, ADD C, ADD D, ADD E, ADD H, ADD L. Fine. So 7 general purpose registers, including A. So 7 different variations. So you can actually add the A with A to give the resultant, and that will again be stored in A only. So moving on now to the flags. All the flags are affected. So you have 5 different flags that we have studied. The sign flag, the parity flag, the zero flag, the carry flag, the auxiliary carry flag. All of them will be affected by this particular instruction. You can set or reset the sign flag by appropriate addition operation. You can set or reset the zero flag. So if you are, say for example, adding 0 plus 0, the result will be 0, so it will set the 0 flag, or it can reset the 0 flag. It is not 0, then it will reset the 0 flag. So all these flags will be affected. JK, then you have the addressing mode. For the source and for the destination. The source, what is the source in this case? Source is the register. So it is register addressing mode. As far as the destination is concerned, it is the accumulator. That is actually implied in this case. So it is implied addressing mode. Then you have the micro RTL. In the micro RTL, you have only the opcode fetch machine cycle. All of this will be same. So whatever has been done previously, it will be same. Fine. So it will be same. Nothing different in this case as well. As far as the opcode fetch machine cycle goes, only in the T4 state, you know that the particular instruction ADDR will be equal to 1. Fine. So this is your first instruction in the arithmetic group, that is add R. It simply adds R with the accumulator and stores back it in the accumulator. Second instruction is ADDM. So this instruction adds the contents of memory location whose address is in M, where M basically stands for the HL register pair. So the address is specified in the HL register pair. And these contents, they are added with that's the contents of memory location with the contents of accumulator and the result and store the result back in the accumulator. Fine. So you can write this as you are adding the contents of accumulator with the contents of HL register pair and storing back the result in the accumulator only. Again, it's a single byte instruction as it occupies only one memory once the instruction itself is consume 1 byte of memory, whereas the HL register pair is an internal memory internal register of the microprocessor. It will be carrying the address and therefore does not consume any space as such. As far as the machine cycles go, there are 2 machine cycles. You have the opcode fetch machine cycle and you have the memory read machine cycle. You have to, once you fetch the address from the HL register pair, then you have to go to that address, read whatever data is at that memory location. So you have 2 machine cycles for that reason. So 2 machine cycle means 7 T states. 7 T states means 2.24 microseconds of time consumed. H, it has no variation. I have an example, like it is in itself an example, add M. Fine. And J, again all flags are affected. So all of the flags will be affected in this case. Then you have the source and the destination addressing mode. For the source, yeah, the memory location that's actually specified in the register. So this is register indirect addressing mode. The source is a memory location whose address is specified in the register, so it's register indirect addressing mode. And the destination is accumulator, so it is implied in the instruction, implied addressing mode. Then you have the micro RTL. You have the same opcode fetch machine cycle, you have the same memory read machine cycle as we have done previously for these instructions. Nothing different, like in case of move a comma m. Similarly, you have for this case also add m, same memory read machine cycle, no difference here. So these are 2 instructions. The third instruction in the arithmetic group is ADI data, again somewhat similar to MVI data. So what does this do? It adds the data immediately provided here. So the data is provided in the instruction itself, and this data will be added with the contents of the accumulator and stored in result is stored in accumulator again. So what does this do? This will add the contents of accumulator with the data that's actually provided immediately. An 8-bit or 1 byte data is provided here. Fine, this is 8-bit data and stored back in the accumulator. So it is 2-byte instruction because add ADI will consume 1 byte, the opcode, and 1 byte will be consumed by the data that's provided here. And therefore you also have 2 machine cycles. You have the opcode fetch machine cycle and you have the memory read machine cycle. With 2 machine cycles, you can say there are 70 states. With 70 states, you can say the execution time is 2.24 of a microsecond. H, there is no variation of this. I, example can be ADD 32H, fine, like that decimal number. ADI 32H. J, all flags will be affected. As far as the addressing mode goes, for the source, the data is provided immediately, so it's immediate addressing mode. And the destination is again the accumulator, so it is implied addressing mode. And the micro RTL, you have the opcode fetch machine cycle, same as we have done in previously, say for example in MVI 32 MVI data case. And memory read machine cycle, again it will be same as in that case what we have done. One thing may be noted about the memory read machine cycles. T1, T2 will be as previously we have done. T3 will be something like this. In the T3 state, we know now read becomes deactivated, it's low to high transition. Whatever was on the data bus, that will not go to the accumulator, that will go to the temporary register, TR. As I previously told you, whatever data we are reading, the arithmetic operations take place like this. Say for example, you have A plus whatever data was in the memory location, or if it is A plus data that's actually immediately given to us, these results are then stored in the accumulator after addition. But first of all, this data M from the memory location or the immediately whatever data is available to us, that needs to be read. So both cases will require this data to be read from the memory. So memory read machine cycle will be involved here. Once the memory read machine cycle, once we read this data, we do not directly add with it. This data is actually then transferred first to the temporary register, and the temporary register is added with the accumulator. That data is stored in the accumulator back. So in this T3 states of the memory read machine cycles, for this case as well as for this case, in the T3 state, the whatever is data we are reading, that will be transferred to the temporary register. Let me write this down for you completely. IO by M bar is 0, S1 is 1, and S0 is 0. Opcode fetch machine cycle will be same. T1, in the T1 state, A15 to A8, the address buses will be loaded by the location of the data byte that's actually available on the program counter. In this case, in this third instruction, ADI data case, in case of ADDM, this instead of this we'll be having HL, because in that case the address was in the HL register pair. In this case the address will be on the program counter. T2, in T2 state, now since this is a read cycle, so read will become activated by making it 0, and the program counter is always incremented in the T2 state. So the program counter is incremented, and whatever was on that address bus, on that location of the address bus, that will be transferred to the data bus now. And now in the T3 state, whatever is on the data bus, first it will be made, read instruction will be made, will be deactivated by making it equal to 1, low tide transition of the microprocessor, and whatever was on the data bus now will be transferred to the temporary register. So after that, this temporary register will be added with the accumulator. That's actually implied, and for that we do not have a separate machine cycle in the microprocessor. So these are 3 instructions. Fourth instruction is ADCR. So what does this do? It adds the contents of accumulator with contents of register R along with carry. Fine. So carry will also be and store the result. And store the result in the accumulator itself. So what does this do? It adds the contents of accumulator with the contents of the register, and depending upon the carry flag, whether the carry flag previously was carrying any carry or not, that will also be added, and all of this will be stored in the accumulator. So it is a single byte instruction because the opcode will only be consuming 1 byte of space in this case. R will not be consuming any memory space. So it also has only one machine cycle because we do not need to read from any memory in this case. So it has 40 states. FG 1.28 microseconds of execution time. H, it has 7 variations, as in case of Addr. ADCR will also have 7 variations. So you can actually list those examples. You have ADCA, ADCB, ADCC, ADCD, ADCE, ADCH, and ADCL. J, all flags affected. K, addressing mode. For the source, you have the register, so it is register addressing mode. For the destination, it is the accumulator, it is implied. And the micro RTL, you have the same opcode fetch machine cycle as usual. So this ADCR, fifth you have ADCM. So the definition of this, adds with carry the contents of accumulator with the contents of the memory location whose address is specified in them, and this stores back the result in the accumulator. Fine. So that's that you can complete this statement. So it adds the accumulator contents with the contents that are available at this memory location whose address is in HL register pair, along with the status of the carry, whether carry is 0 or 1, that will be added. So this carry will have been actually being carrying from the previous instruction. This carry can be carried forward, and all of the result will then be stored in the accumulator. So again, it's a single byte instruction. Two machine cycles, single byte, two machine cycles. And what are the two machine cycles? You have the opcode fetch machine cycle and you have the memory read machine cycle. 70 states. .24 microseconds of execution time. No variation. Example is itself ADCM. J, all flags affected. JK, the addressing modes. Source is register indirect. Destination is implied. And then you have the micro RTL, you have the opcode fetch machine cycle and the memory read machine cycle. Same. There will be no difference between ADDM and ADCM. There will be no difference in the micro RTL of ADC because the carry is not something that we are reading in this case. It's actually carried in the microprocessor itself. Similarly, you have sixth instruction, that is ACI data. So like ADI data, we have now ACI data. So what does this do? Adds with carry the data that's immediately provided with the contents of A and stores that in A. So whatever is in A, that will be added to the data that's provided here, along with the